Okay, welcome everyone to another edition of Symmetry in Newcastle. The speaker of today is Mari Elder from University of Technology in Sydney, and he'll be talking about rewriting systems and geodetic graphs.
Thanks, Mikhail. I was just going to show you there's your old desk. Okay, so I'll be using the iPad. You can leave your camera on if you like, because I've got everyone's camera on my screen so I can see if there's any question. So today I want to talk about new joint work with Adam Piggott, who is here, concerning rewriting systems and geodetic graphs. So the plan is to talk about geodetic graphs, which is graph theory, plane groups, which is group theory, and finite convergent length reducing rewriting systems, which is computer science. And what on earth do any of these things have to do with any other? Anyone know? Then I can stop if you already know. Geodetic graph. So delta is a simple undirected graph. And a path in this work, we're going to consider a path in this graph to be a sequence of vertices, which we might visualize by a path like that. U0 up to Un of length n. So every connected graph, just like a Calligraph is connected, is equipped with a natural metric where the distance between two vertices is the shortest path between them, connecting them. And that's called a geodesic. Okay, I've been saying geodetic too often. So the shortest path between two vertices in the graph is called a geodesic. And then delta, the whole graph, is geodetic if the geodesic between any 2 points is unique. So like a tree would be geodetic because the geodesic between any 2 points is unique. Okay, so here's an example that you can take a screenshot and play with if you want. So between any point, maybe x1 and x2, what's the shortest path? Length 3, too long, so it can be a bit tedious to work it out. But you have to check every pair of vertices and to check whether there's a unique shortest path between every 2 points. Here's another example. It's just a graph at the moment. So you've got some triangles in it. So there's loops. It's not just a tree, but between any 2 points, you can check that there's a unique geodesic. Okay, so that's a geodetic graph, and this is not a geodetic graph because I've got squares. And so I've got 2 ways to go around that square. Oh, let's zoom out again. A path in any simple undirected graph is called an embedded circuit if the vertices as you go around the path are all distinct, and then the first vertex is equal to the last vertex. And so some people might just call that a circuit. I'll call it an embedded circuit. So here's the first quiz. If you've got a geodetic graph, then what can you say about the length of embedded circuits? So I've got an embedded circuit.
I can get this one. It has to be odd.
Mikhail wins the first prize. I'll just send it in the mail. Has to be odd. Why, Mikhail? Here's an embedded.
If it were even, there would be 2 ways to go around.
But there might be a problem with this quiz because I didn't say it had to be the shortest. So it's just a circuit. So for instance, So it's a trick quiz. That's a complete graph. Yes, so you lose your prize, Mikhail. It's a trick quiz, which I think Adam pointed out to me 5 minutes ago when I sent him the slides. No, like an hour ago. So it's not an isometrically embedded circuit. So that's the purpose of my first evil quiz there. So this is the complete graph on 4 vertices, and there's an embedded circuit, and it's got even length. So what Mikhail answered was the same quiz 2 when we talk about isometrically embedded circuits. So an embedded circuit is isometrically embedded if the subgraph comprising of the vertices in the circuit together with the edges between consecutive ones is convex in the metrics, in the distance of the graph, so that there's no shortcut that's outside of the circuit. Okay, so I think that's what you're thinking, Mikhail, isometrically embedded circuit. So now if I ask quiz 2, which I haven't got, the same question, the length of isometrically embedded circuits. Mikhail?
Has to be odd.
Oh, very good. Awesome. Are we recording this for YouTube? I hope not.
Yes, we are.
You're going to edit that bit out later. No worries. No. Okay, so how are we going here? Yeah, so it has to be convex. So that as you're going around either side of this circuit, the shortest distance in the graph is realized by going along the circuit, although it could be in a non-geodetic graph, so there could be many different ways to go. Okay, so there's some graph theory that we get started with. So here's a cool fact. If you've got a geodetic graph and you've got 2 paths, which I'll just draw and get bored of drawing that, 2 paths. So they're equal length geodesics, and the distance between the endpoints is 1. So I'm in this situation. And actually they may have some common prefix, but then at a certain point they diverge and the distance between the endpoints is 1. So in this situation, as you go around, but hang on, I just said U0 can be the same and U1 and U1 prime have to be different. I better read my slides more carefully. So in this situation where there's no prefix, then going around that circuit is isometrically embedded. So there's a nice exercise to prove. Or you can go and find Andrew Eveleigh Price's master's thesis from Melbourne Uni. Okay, so that's a fact. So geodetic graphs go back a long way. So Orr has a textbook, Theory of Graphs from 1962. George, do you have a copy of this? Michael?
No, I don't.
Ah, okay. So one of the challenges in Orr's book is to classify the geodetic graphs. So obviously we already saw one. Every time you have a complete graph, I'll go that way, a complete graph, that's geodetic because there's a distance 1 between every 2 points. But what else can you have? So that's the question. So it's a very old question, so surely we know by now. So rather than trying to do the whole classifying, how can we build them? So here's a trick that Adam told me, that you can always start with a complete graph. I wanted to go over the top and draw that very well. You can always start with a complete graph and do the following trick. So you can put integers at each vertex of the complete graph. So I'll just choose those integers. And then you put, this has got the integer 1, so I'll make a new vertex, just one new vertex, because the number 1 is there. And this is also a number 1, so I'll make a new vertex there. Okay, so that's a cute little thing to do. So I could have put 2 there and I'd end up with 2 vertices there. So no matter what choice of integers you place, this is always ends up being a geodetic graph. So that was actually my original example. So that's another little fun thing to prove. Okay. So let's move that picture again. So that's graph theory, but in '97, Shapiro, Mike Shapiro asked this question: what groups admit geodetic calligraphs? So we may as well consider, we normally think of calligraph as directed, so let's just consider the undirected version of the calligraph. Okay, so obviously the free group is going to give us a tree. And you might immediately say virtually free group, because that's the theme of today, I'm told. But a virtually free is going to maybe have, in general, lots of ways to go around. So that was Shapiro's question. So let me say one more thing. I'm going to define blocks. So if you've got a vertex in one of these graphs, the vertex is cut vertex if the graph is connected, but if you remove this vertex, then suddenly the graph is not connected. And a graph is two connected if it's connected. Is that right? And has no cut vertices. Yeah, that's what I want. The maximal two connected subgraphs. So take a graph and take all of the subgraphs you can think of and look at the ones that are two connected, and by adding any other vertex to that, it's not two connected anymore. So let me give a picture. So the maximal two connected subgraphs of a graph are called the blocks. So in this case, if I remove one of those vertices, it'll be disconnected, so I wouldn't want to include that edge. But otherwise, that's they're my blocks. Okay, just recycling my TIX pictures. So it follows from the maximality of the block that any block B, if you're a block, then you're the induced subgraph of the vertices of that block. Okay, so that's maybe enough graph theory for everyone, because I promised 3 different fields of research. So here's one more lemma. Let delta be the same graph as usual. 2 vertices lie in the same block if and only if, so those guys look like they lie in the same block, if and only if there exists an embedded circuit that visits both. Okay, whereas if you've got one in here and we think that those two are not in the same block, then there's no embedded circuit because I'm going to have to cross that edge. That's not a difficult thing to prove. So there's a connection between blocks and embedded circuits. And just a little observation that these vertices that I was interested in before, I should change color. Those vertices lie certainly on an embedded circuit, but Mikkel, if I gave you the quiz 3, find an isometrically embedded circuit for them to lie on, well, that's not going to be possible in this case. So that's my introduction about, no, graph theory continues. One more thing. The block cut tree. So given a connected graph, the block cut tree is something we can construct, always construct. So you put a vertex, you say of type 1, for each vertex of the existing graph. And then you put another vertex for every block. And you join 2 of these vertices of type 1 to vertices of type 2. If that vertex, that green vertex, lives inside that block. And so that block will be connected to all of the green vertices inside it. So given any graph, you can look who are the blocks and you can construct this big thing, and it's a tree. It's an exercise to prove it's a tree. Well, how could you have two different ways of going around via two different blocks? That would be problematic. If you somehow had a loop, it would mean you managed to travel around via two different blocks. Okay. So anytime you have a connected graph, you can write down this block cut tree. Okay, so this is normally a group theory seminar, so I think 20 minutes of graph theory at the beginning is maybe pretty tough. So let's go to group theory. And this is possibly a terrible name for a class of groups because no one's going to be interested in a plane group. So there's another name for them, the basic groups, which doesn't really help us at all. So a group is called plane if it's isomorphic to the free product of finitely many factors. So G1, free product G2, Gn, where each factor is either a finite group or just Z. So that's a plane group. Okay, so if they're all Z's, you just have a free group. Okay, so there's several. So here's an example. This is C2 star C3. So I had that picture before.
Murray?
Yeah.
Would it be correct to say that group is plane if its decomposition as a graph of groups is that the vertex groups are finite and the edge groups must be trivial?
So quiz 4, what would it mean to be plane in terms of Basset theory? Oh, can't see. You're desperate to win as many prizes in this talk as possible, Mikhail. So, of course, that's one characterization of plane groups that comes from Basset theory. So there are special, we can see immediately from this that they're a subclass of virtually free groups. They're the ones that are acting on some tree, locally finite tree, with trivial edge stabilizers, so that you don't get any H and N's and amalgamated free product. So that's one way to say that they must be interesting. There's some language theory characterizations of them, and maybe there's many different characterizations. Okay, so that's a plane group. Thank you, Mikhail, for preempting that. So I want to give this connection between plane groups and calligraphs and their calligraphs. The following are equivalent for any integer s, positive integer. So the group admits some finite generating set so that the undirected calligraph, so just glue together x and x inverse as a single undirected. So in this undirected calligraph, the diameter of any embedded circuit is at most s. So you've got maybe that picture that we had on the last one, you try and draw an embedded circuit, the diameter of that circuit would be at most 1 because you only had triangles. So the second one is that G admits probably the same choice of finite generating set, so that in this thing, the diameter of any block is at most s. So actually, we've already seen that any two vertices lie in the same block if and only if they lie on some embedded circuit. So the diameter of the circuit will be, in worst case, the same as the diameter of the block. So those two we've already seen. And the third one is that G is a plane group. So does anyone want to predict the proof of this one?
What about finite groups?
That's plane, you just have one factor.
Oh, okay, you're allowed any finite group, yeah. There's a factor.
Yeah. Mm-hmm. quiz number run out. So finite groups, no problem. So the 1 and 2 are equivalent because we're already seeing blocks and embedded circuits are related. But the proof connection between the Calligraph and the plane group is the way that Adam and I like to prove this is through the Bassett tree. Sorry, the block cut tree. So you create the block cut tree of this Calligraph, and then the group acts on its own Calligraph, so it also acts on its block cut tree. And then you just, because of the blocks, they're not going to get, they're going to have trivial stabilizers. So the edges in this block cut tree will have finite vertex stabilizers and trivial edge stabilizers. So this characterization was known earlier, but this is sort of the modern way to think about this. Okay, so that's going to be something I'm going to need, but I haven't told you where I'm going. I'm just randomly telling you different things. So the proof, I kind of said it in words, so let me. So I'm still randomly telling you about things that I think are cool and maybe don't have any connection with each other. So here's the last one. Rewriting systems. So now we're in computer science. So a rewriting system is something that has an alphabet, sigma, and T, a set of rules. Okay? So it's an alphabet and a set of rules, and that's it. It's a pair, sigma and T. Okay, so what is a rewriting system? It's just a pair of those two things. The set of rules, rewriting rules, T, determine a relation on the set of all strings that you can form out of those letters, finite strings. So A goes to B if A is equal to U something B, and B is equal to U something else B, where L and R were one of the rules. So it's a rewriting rule. You take a string, and if you see one of the left-hand sides of the rule, you can replace it by a right-hand side of the rule. So no other restrictions at the moment. So if RL was also in T, I could apply that. And I could just keep going forever, which would be kind of useless. So I can see everyone's videos, and Adam just has his permanent photo there of him just looking at me in a very disbelieving way. It's quite off-putting. I might put a book or something in front of it. Sorry, I'll carry on. So let's get moving a bit further. The reflexive transitive closure of just applying a single rule is that you can get from one string to another string by applying lots of rules. Okay. A word is irreducible if there's no left-hand side factor visible in the word. Okay, so computer scientists for many years have been interested in these processes, these things. And then the reflexive transitive symmetric closure of this is an equivalent relation, and we denote it by that symbol. So the set of all words you can get by going either way, either reducing downwards towards something or going backwards. They're all considered to be equivalent to each other with respect to the rewriting system. So then on top of that, we throw the operation of concatenation, and we see that that gives us a monoid. So you've got the set of all equivalence classes of things that you can reduce and get between each other. And if you concatenate two representatives and then reduce it to something, then you could have reduced first and then gone. So there's a little bit to do there. So any rewriting system corresponds to some monoid over that alphabet. And if that monoid happens to have inverses for everything, then we'll get a group presented by a rewriting system. So there's a connection there. Okay, so I think it's time for a quiz. I've numbered it too, but I've had many. Here's an example. I've got little a and big A. And the rules, you can take a little a and a big A as a subword and replace it by the empty word, which I've called 1. So the equivalence class of all words with A's big and small, where if you ever see an A with a big A, you can delete it. Or you could add one back in again if you want in the equivalence class. And then if you concatenate 2 such words, you end up in a different equivalence class. So can anyone tell me what group or monoid this presents? I'm not
The infinite cyclic group?
Thank you, Colin. I've been trying to do a lot of teaching on Zoom and trying to get a rise out of anybody in the Zoom room is always quite difficult. Thank you, Colin. It's just basically the free group. Oh, am I still sharing?
No, you're not.
Okay. Someone else is trying to. How's that?
Yeah.
Cool. Great. So it's simply the set. It's a weird way to think about the infinite cyclic group, maybe, but that's what we get. Okay. And so from this example, you probably think, how would I do the free group of rank 2? You just have A's and B's and the set of all equivalence classes with those rules. So the next quiz is still there. Oh, that was the answer, in case nobody got it. Now I've got G as any finite group, and I'll take the alphabet to be everything except the identity element of the group. And now my rewriting rules are going to be 2 elements of the group is going to turn, on the left-hand side, gets replaced by 1 element of the group. And that's allowed for any time that G times H equals K in the group. Okay, so it's a bit contrived that I'm just beginning with a group, but turning it into a rewriting system and then asking what kind of group do I get out of it. So there's a bit of a hint there for you. And also G times H gets replaced by the empty string if actually H inverses G. So I won't insult everyone's intelligence. You'll get the finite group back again. So if it was an infinite group, this would work as well. I just have this massive multiplication table encoded by a rewriting system, but it wouldn't be a finite rewriting system, which is a bit ugly. Okay, so I've just encoded the multiplication table by that. So free groups, you could pretty quickly get from that example, are presented by finite rewriting systems, but there's one other special thing about this rewriting system. They're length reducing. It's length reducing. So every time you apply a rule, the length of the word goes down. So that's a special property. And there's a few other special properties. So here's some adjectives that we say in front of rewriting system. Finite if the sets are finite. Terminating if there's no infinite sequence of factor replacements. Okay, so in this case, because it's length reducing, we know that there's no infinite sequence of factor replacements of the individual one. And sometimes if it's not length reducing, that's a little bit tricky to actually prove that property of some rewriting system, that you couldn't come back around to where you started. And length reducing if the left-hand side is always bigger. So the examples of the finite group and the free groups are all finite, terminating, length reducing rewriting systems. 2 words are called joinable. if you've got X in the alphabet and Y in the alphabet, and you can reduce by a sequence of, oh, we have a symbol for that, reduce to the same word. So you might have two freely unreduced words for some group element in the free group, and you reduce to the same freely reduced word would be an example. So joinable, and a rewriting system is called confluent. If you ever have the situation that W gets reduced to X and W gets reduced to Y, then I need a better picture though. I'm sure I could do a better picture than that. Then if they branch out, then they have to come back again. But I'm not happy with that picture, so I think this is a better one. So you're at hexam, so W equals hexam, and then you can go two different ways around Kurunang Island, watching out for the what's the chemical that you have there? That's okay. It's just my
ammonium nitrate.
Ammonium nitrate. My little shout out to Newcastle. Cool. So you can branch out, but then suddenly this river is confluent. That's the confluence of the two rivers in English. Cool. So we have all these adjectives, and finally a rewriting system is called convergent if it's terminating and confluent. So if you're ever applying these rules and they start branching in two different ways from a single W, then they're guaranteed to come back. And apologies for everyone who knows all this very well. And also you want it to be terminating so that the rules just don't go around and around together. Okay, so if it follows that a convergent rewriting system, you could branch out and come back again. So you always end up with a unique normal form for each, a unique normal form representative for each equivalence class. And if it's length reducing, you end up with a geodesic representative for each equivalence class. So it's a nice thing to have a finite length reducing convergent rewriting system. So they come up, even though it's a mouthful, it's quite a natural thing to have. So here's a lemma, F's, whatever. All of those adjectives in a rewriting system implies you've got a geodetic graph. Okay, so Calligraph. So if a group is presented by one of these systems, then suppose you've got two geodesics going between the same vertices. Well, there's a convergent length reducing rewriting system. So this guy is a geodesic. It can't possibly have the left-hand side of any rule because you could make it shorter. If this had a left-hand side of some rule, suddenly it would become shorter. But this guy is another geodesic, and so also it can't have. So you've got two words that can't reduce together. So therefore, it fails one of those adjectives that we had before. Moreover, if the left hand, and this is just a technical thing that I want to use when I get to what I'm talking about, which is very soon. If the left-hand side of the rules have length at most s plus 1, so the example we saw for the free group or the finite group was that the rules had length 2. So if you've got left-hand side length at most s plus 1, then the isometrically embedded circuits in this geodetic calligraph, well, it's odd length, so I'll draw it like that, where these have the same side length. So it's an isometrically embedded circuit, it has to have odd length. Well, and then this is length n and this is length n. So in this situation, this word going there and then down has length n plus 1. So it's not a geodesic. So therefore, because we're in this convergent length reducing rewriting system, there must be a shortcut. There must be a left-hand side of a rule. So maybe the left-hand side of the rule is here, but if I applied here, it would be shorter. So therefore, the left-hand side of the rule has to be at the end. So I'm doing a picture proof, pure geometric group theory. So where can there be a left-hand side of a rewriting rule? Has to be at the end. So therefore, there's something shorter here. So if this was the maximum length s plus 1, then this is at most s. And Stefan is nodding. So I'm going to take that as a... So now that's fine. So now that's a geodesic, but that's a geodesic. Oh, I've got two geodesics to the same place. Therefore, the whole thing had to have just been that bit there. It takes a little bit, but I wanted to give you just the first flavor of how these arguments will go. Okay, so if my left-hand sides have a certain bounded length, then that tells me something about the isometrically embedded circuits. And don't make the mistake that Mikkel made to just talk about general embedded circuits, because we can't say anything about it, a general embedded circuit. Okay. So I'm very happy you made that mistake, Mikkel, because I'm going to exploit it all the way to the end of the talk. Not just to
be my guest.
So, so that's, sorry if that's a bit of a rough and ready geometric group theory proof. Okay. So one more thing about rewriting systems for now. Suppose that I have, it's just a pretty straightforward lemma for people to prove. Suppose you've got a whole bunch of rewriting systems over disjoint alphabets, and they all present different groups. Well, the free product of all those groups is simply the union of all the alphabets and the union of all the rules. There's no overlap with the rules. So for instance, the free group, you'd have the one generated by AA, and then another one generated by B and B, etc. And you just combine them. So what does this tell us, this lemma? Well, we already know that a Z has a finite length reducing rewriting system with sides of length 2. And finite groups all have finite convergent length reducing rewriting systems where the left sides have length 2 as well. And now free products of any collection of groups that we already know also have one of these rewriting systems. So we get this corollary, that if you're a plane group, then I can give you an explicit blah, 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 length reducing rewriting system. And moreover, the left-hand sides are equal to 2 because that's the one that I chose. Where am I going with all this? So I think now, yes. What's the big picture? So I've told you about 3 things: geodetic graphs, plane groups, and rewriting systems, and given little hints about how they might be related to each other. Madlena and Otto, in about the 80s, asked the following challenge in one of their papers. Can you come up with a complete algebraic characterization of the groups that are presented by length reducing rewriting systems? So many people in computer science were interested in these length reducing rewriting systems and others. So what's a complete characterization? So what would be a possible answer? Well, Gilman made this conjecture. If you've got a group, then a group admits a presentation by finite convergent length rewriting, I should have used the abbreviation, in which the right-hand side of every rule has length at most 1. So Gilman was not trying to do well, it's a conjecture. So he was saying, can we even do this? What if the rewriting system just have every rule suddenly goes to either the empty word or just a single letter. So surely we would be able to do that, right? From 1984. And then in general, for general length reducing, we'll have to think harder. So that was Gilmans' conjecture, around since 84. And Madeline and Otto, 87, prove that if you've got, no, they didn't prove. It's a conjecture, sorry. So Gilman's conjecture is just if the right-hand sides have length 1, and the big conjecture here, generalizing Gilman's conjecture, it's a bit out of order, this slide, that G omits presentation by a finite convergent length-reducing rewriting system if and only if the group is plane. And Gilman also is plane. Okay, so we know one direction, that if you're plane, then we have a length-reducing rewriting system where the left-hand sides have length 2, so of course the right-hand sides have to have length 1 or 0. They do, because we saw it. So that's the connection. So in 2019, Adam Piggott and his collaborator, Andy Eisenberg, proved Gilman's conjecture many, many years after it was put out there. So they proved it where the right-hand sides are all length 1 or 0. So it's quite a special case of the big conjecture. But then, this is our theorem. So let G be a group. G admits a presentation by a finite convergent length reducing rewriting system, caveat number 1, such that the generating set is symmetric, which was not part of the Gilman's conjecture. So that's caveat number 1. And caveat number 2, and the left-hand side of every rule has length at most 3. Because Gilman's conjecture tells us if the left-hand side has length 2. So what we've done here is we've pushed the boundaries of this area by 1. We've added 1. So I'm pretty impressed, but I leave it to the audience. And the proof, which I've got a few minutes, but my goal was to give you all the definitions, maybe give you some little glimpses of what's going on. And then I don't have to embarrass myself with giving too much of the proof. So is it clear? That's our theorem. So our proof is actually via geodetic graph theory. So the backwards direction is already done. If it's plane, we've explicitly got a rewriting system, as I have outlined. So that's fine. And the rewriting system where every left-hand side has length at most 2, which is at most 3. So we're good. So this is the forwards direction of this proof. So up above, we've got, if you've got this finite convergent length rewriting system, then that gives us that the undirected Calligraph is geodetic. And remember that if the left-hand side was length S plus 1, then the isometrically embedded circuits had to look like S, S, 1. So the answer to this quiz is 2S plus 1. So what's important is that there's some bound. So if you've got, oh, hang on. In general, if you've got the left-hand side S plus 1, then the isometrically embedded circuit has length at most 2S plus 1. It can't be longer than that. Because if it was longer than that, why is this not a geodesic? Well, there has to be a rule that applies. That was the argument before. So in this case, we have the left-hand side at most 3. So here we get 2S plus 1 is 5. So we're in a situation where our hypothesis tells us that we've got an undirected geodetic graph, which happens to be a calligraph, but we don't care about that anymore. Happens to be a calligraph, but it's an undirected geodetic graph where the isometrically embedded circuits have length at most 5. So what could that possibly be? How hard could that be to say something about? Now remember Michael's famous error at the beginning of the talk, where we mixed up embedded circuits with isometrically embedded circuits. So at this point of the proof, isometrically embedded circuits have length at most 5, and it's a locally finite graph because it's a Calligraph. So that would tell us the diameter of these isometrically embedded circuits is bounded. And then if you can recall, having a bound on the diameter of, what were they? Mikhail, were they embedded circuits or were they isometric? Well, if we go away, unfortunately, the most 5. So if we could connect this up to say something about the diameter of just embedded circuits, then that theorem from before about blocks and the block tree implying plane, that was about embedded circuits. So that's why I'm very impressed with that error, because it's actually the real guts of what we have to prove. Our hypothesis tells us that there's a bound on the length of isometrically embedded circuits, and we somehow need to say, okay, that implies a bound on just embedded circuits. And once we have a bound on the diameter of embedded circuits, we can build the block cut tree and say that it has finite stabilizer, etc., and you get plane. So that's the big picture of the proof, and it's all boiling down to, I've got a geodetic Calligraph with isometrically embedded circuits of mode 5. What can I say about embedded circuits? Well, this is what we can say. Theorem 2 is that if you've got, as I just said, where the circuits have length 5, then actually the embedded circuits have diameter at most 2. And that gives us our proof. And then you'll be saying, well, okay, if the left-hand side of the rewriting rule had length, what was it, most 3, so now it's at most 4, then we would need a similar theorem to just give us some finite bound on the length of isometrically embedded circuit. So that's what's going on. And so this turns out to be the real difficult bit. So the proof strategy, but I think I'm almost out of time, is assume you have assume the hypothesis, and then assume you have a embedded circuit with a big diameter, at least 3. Argue a lot about this particular minimal counterexample, and then get a contradiction. And arguing about that means drawing a million pictures of tiny little graphs like I had at the beginning of the talk. So it's really fun. So slightly more detail is here, that first of all, if you've got one of these minimal length counterexamples, then it actually goes around here. Then it contains a geodesic subpath of length 3, kind of realizing the diameter. And then once you have that, you do lots of arguing and use some old results of Stempel, who classified geodetic graphs of diameter 2 and did various things like this. So you do lots of arguing and you end up seeing pictures like this to say, oh, that can't happen, that can't happen. This minimal example has to look like this, and you get a contradiction. So final words. So the theorem 1 about rewriting systems falls well short of the conjecture or the question to give a classification, but we believe that the classification is the only thing you could possibly get is plane groups. And we think that what we have here, which will be on archive very, very soon, what we have here maybe shows how far you can get with the graph theory approach, because it boils down to a very obnoxious kind of argument about finite graphs. Or maybe you can push it further. So that's all I have. Thanks, everyone.
All right, thanks, Murray. It was a really nice talk. Are there any questions for Murray?
Good.
Well,
Adam stopped that smirk that he has on his photo. I'm happy about that.
so if there are not any further questions, let's thank Murray one more time. we have a coffee break now.